Okay, let's look at section 2, 2.2, and this one is the the inverse of a square matrix. So let's start from the first one, 1.1. What is the inverse of a matrix? The definition: an n by n matrix A is called an invertible matrix if there exists an n by n matrix B such that AB is equals to identity n, which is the same as BA, the same as BA. So in this case, we usually write the inverse as. So that is the inverse of a matrix. That is the inverse. So when you multiply the matrix by an inverse, its own inverse, then you get the identity matrix. So if the matrix is an n by n matrix, then the identity matrix that you get is also an n by n. It's also an n by n. Now, if the matrix B is, if that matrix is not invertible, then it means it is a singular matrix. So we can say the matrix B is called the inverse matrix of A if A is not invertible matrix. Then we say it is a singular matrix. It's a singular matrix. It's a singular matrix. So if you don't find the inverse of that matrix, then it is a singular matrix. So it means if when you multiply the inverse by the same matrix and you don't find the identity, then it is a singular matrix. It's a singular matrix. Okay, let's look at theorem number 1. Theorem. If A is an invertible matrix, and this one is n by n matrix. If A is an invertible n by n matrix, then the inverse of A is unique. The inverse of A is unique. The inverse of A is unique. So how can we prove this? Now, let's prove this. Now, suppose that B and C are inverse matrices of A. Inverse matrices of A. Then if C is the inverse matrix of A and also B is an inverse matrix of A, then C is the same as C multiplied by the identity N. So C is the same as C multiplied by the identity N. And you know that to get the identity In, then it is the same as, so this is actually the same as C. And we know that A, B are what? A and B are, so B is the inverse of A. So to get this identity, then you multiply A and B, so it's the same. Then also, this is the same as CA multiplied by B. So it is the same as multiply C and A. So to get C, so CA is also the inverse of A. So therefore, C multiplied by A is the same as INB, which is equals to. So therefore, it shows that the inverse of the matrix is unique. So it is unique. Okay, let's look at example number 1. How do we get to multiply the matrix by its own inverse? But before we look at that, let's look at a notation on how we put this as inverse. Now, if A is an n by n, which is invertible n by n matrix, then we denote the inverse of matrix A by A, and then so then it means that when you multiply A by A inverse, then you get IN. A inverse, you get IN. Or also, when you multiply A inverse by A, you also get IN. Okay, let's look at the first example. Example number 1. Now, show that B, which is equals to 2, 1, 3, negative 2, 1, negative 6, 1, negative 1, 4, and the inverse matrix of A equals to negative 2, -7, -9, 2, 5, and 6, and then 1, 3, and 4. Show that B equals to that. Show that B, which is this, is the inverse matrix of A. Is the inverse matrix. So how should we show this? So what we need to do is, so the solution. So we need to get BA and AB. So we want to see whether AB and BA will give us the identity matrix. Will give us the identity matrix. So we want to show that BA and AB should give us the identity matrix. So how can we show this? So we need to multiply B by A and then A and B. So our BA is the same as 2, 1, 3, -2, 1, -6, 2, 1, -1 and 4, multiplied by -2, -7, -9, 2, 5, and 6, then 1, 3, and 4. So when you multiply this matrix by row and column, so either way, you can use the row column, or you can use the one which you multiply the matrix and the vector. Matrix and the vector. So in this case, let's use the row column here. So 2 multiplied by -2, you get -4. 1 by this. So you get, so the first one is 2 multiplied by that, you get -4, right? And then this and this, you get +2. And then this and this, you get +3. So -4 plus 5 is what? Is 1. We come to the next one, 2, and this one is -14. This and this is 5, so -14 plus 5. And then this and this is 3. So it gives us, all this should give us 0. This should give us 0, 1, 0, and then 0, 0, and then 4. Should be like that. Also, our AB is the same as -2, -7, -9, 2, 5, and 6, 1, 3, and 4. Multiply this one by 2, 1, 3, -2, 1, -6, 1, -1, 4. So what do you get? So you multiply the first one, -2, and this one will give us -4, this and this. So -4 and plus 14, and then -9. So that should give us 1. And then the others are zeros. So it should be like that. So therefore, AB is equals to B. AB is equals to BA. So it means when you multiply the inverse by matrix, is the same as multiplying the matrix by the inverse. So it commutes. It commutes. Okay, let's now look at 1.4, which is invertible. 2 by 2 matrix. Invertible 2 by 2 matrices. Now, if we have the matrix, which is a 2 by 2, how should we get the inverse of a 2 by 2 matrix? So the determinant of a 2 by 2 matrix A, which is the same as A, B, C, D, is what? So how should we get the determinant? So the determinant here is determinant of A is equals to, is actually the same as, we can actually write like that. The determinant of A is the same as getting the determinant of A, B, C, D, like that, which is equals to multiply across, so AD minus CD, AD minus CD. Now, number one, if determinant of A is not equals to 0, then A is an invertible matrix. And A inverse is the same as 1 over determinant of A. Multiply this by D minus B minus C and then A. So to get the determinant of, to get the inverse of A, then what you need to do first is to get the determinant. So you have 2 by 2. Then get the inverse, then you multiply by 1 over the determinant. And then what you need to do is you interchange A and B, so you interchange, and then the two opposite ones, you put them negative. So you interchange A and B, and this one. So A inverse is equal to 1 over the determinant, and we interchange those, and then you put the negatives on the opposite side. Now, number 2, if determinant of A is equal to 0, then A is a singular matrix. A is a singular matrix. Now, we can prove this, but it's not of any mean. What you need to remember is you get a determinant of the inverse of 2 by 2 matrix is 1 over the determinant. You interchange B and A, and then put them on the opposite side. So let's do an example on this. So you can look at your book for the proof. So here, the only thing you need to check is if A is equals to A, B, C, D, then our B is the same as 1 over determinant of A, D minus B minus C and A. So what you need to check is you need to look at, when you multiply A and B, then it should give us what? 1, 0, 0, and 1. So what that is how to prove the factor. So you have this A and this one, and our B is this. Now, when you multiply the two, then it should give us the matrix. Okay. Now let's look at an example on this one. So let's look at example number 2. example 2. Now, if we let A to be equals to 1, 2, 3, 4, and B to be equals to 1, -1, -1, and 2. Now, number 1, find A inverse and B inverse. So find A inverse, B inverse. So we know that to get A inverse, then it is the same as 1 all over determinant of A, and then you multiply this by A, which is our A here is what? You interchange this and this, which is 4 here and 1 here, and then you put the negatives, -3 and 2 there, -3 and -2. 3. So what is a determinant? So our determinant of A is the same as 1 multiplied by 4 minus 3 multiplied by 2, which is giving us 4 minus 6, which is minus 2. Which is minus 2. So then our A inverse is equals to 1 over -2, and then 4, -2, -3, and 1. Which is the same as what? You now distribute that constant there, which is the same as -2, because you multiply that and that, you get 1 here, you get 3 over 2 there, and then you get -1 over 2 there. So that is our A inverse. That is our A inverse. Join together there. So you just distribute this. So multiply this and this, you get -2. Multiply this and this, you get 1. This and this, you get 3 over 2, and then this and this.
So do we give an absolute value when we an answer, or what happens in absolute value?
No, it is not the absolute value. It is actually the determinant.
Oh,
Yeah. So when you put like that, then it means it's the determinant. Yeah. The determinant. It's not the absolute value. So instead of writing determinant of A, then what you can do is you just write like that. Okay. Yep. Okay, now let's get B inverse. So our B inverse is the same as 1 over determinant of B, and then you multiply by 2 and 1 here, and then 1 and -1 there. 1 and -1. So you switch. You switch this and this. Switch this and this, and then you put negatives. Oh, this one was negative also. So this is actually positive. So what is our determinant of B? So our determinant of B is equals to 2 multiplied by 1 minus -1 multiplied by -1. Again, make sure you remember those signs because everything. So 1 multiplied by 1 is 1. So this is equals to 2 minus 1, which is equals to 1. Is equals to 1. So our B inverse is the same as 1 all over 1, 2, 1, 1, 1, which is equals to 2, 1, 1, 1, 2, 1, 1, 1. Okay, that's it. That's how to get the determinant of the inverse 2x2 matrix. Number B. Find AB inverse, A inverse, B inverse, and B inverse, A inverse. B inverse, A inverse. Okay, now let's get AB. So you multiply A and B. So AB is the same as 1, 2, 3, 4 multiplied by 1, -1, -1, and 2, which is giving us, so our AB is equals to -1, 3, -1, and 5. So that is our A. Is our A. Now, what is the AB inverse? So our AB inverse is the same as 1 over determinant of AB, and then the inverse here. This will now be 5, and then -1 here, and then 1 and -3 there. 1 and -3. So determinant of this, determinant of AB is equals to this, and this is -5. And then now this and this is -3, so plus 3, which is equals to -2, which is equals to 2. So then this is the same as 1 all over -2, 5, -3, 1, -1. And this is giving us -5 all over 2, 3 all over 2, -1 all over 2, and then 1 all over 2. So that is our AB inverse, our AB inverse. AB inverse. Now, what is A inverse, B inverse? So we already have A inverse, B inverse here. Let's multiply. So A inverse, B inverse is equals to A inverse is -2, 1, 3 over 2, -1 over 2. Our B inverse is 2, 1, 1, 1. So that is our B inverse. So what do we get there? So when you multiply, then this and this is -4. That and that is 1. -4 plus 1 is -3. So the next one is -1. The next one is 5 over 2. And then the last one is 1. Last one. So this is 6 over 3. 3 plus this is 3 minus 1 over 2. 3 minus 1 over 2. Okay, now what is B inverse A inverse? So what is B inverse A inverse? So this is the same as 2, 1, 1, 1. And then our A is -2, 1, 3 over 2 minus 1 over 2. So what do you get? So what you get here is when you multiply this and this, it is giving us -4. That and that is 3 over 2 minus 4 plus 3 over 2. This should give us minus 5 all over 2. This should give us 3 all over 2, minus 1 over 2, and then 1 all over 2. All over 2. So we will see something from here. So what can we see from here? We can see that our AB inverse, which is the same as this, is equal to the inverse A inverse. So what you can see from there is our AB inverse is the same as B inverse multiplied by A inverse. If we recall the transpose, say our AB transpose is the same as B transpose multiplied by A transpose. That is what we said. So it is similar thing. It's actually similar. So A inverse, so it is not equal to, so A inverse is not equal to A inverse. So it is not. So let me write it here. So AB inverse here is not equals to A inverse B inverse. It is not equal. So make sure you remember that. Any question up to that? Number C. Number C. Find A transpose inverse and A inverse, then transpose. A transpose inverse, and then A inverse transpose. Okay, so we have our A to be equals to 1, 2, 3, and 4. So what is our A transpose? Then A transpose is equals to, you interchange the rows and columns. So 1, 2, and then 3, 4 there. 1, 2, 3, 4. So that's A transpose. Now, what is the inverse of A transpose? So the A transpose inverse is equals to 1 all over the determinant of A transpose multiplied by 4, 1 here, right? And then negative 2 and 3 there. Negative 2 and negative 3. So you interchange 4 and 3, 4 and 1, and then put the negatives. So what is the determinant of A transpose? So determinant of A transpose is equals to 4 multiplied by 1 minus 2 multiplied by 3, which is equals to minus 2. So then A transpose inverse is equals to 1 all over minus 2 and 4 minus 3 minus 2, 1, which is the same as minus 2, 3 over 2, 1, and then negative 1 all over 2. Negative 1 over 2. That's what you get. Okay. Now, what is A inverse transpose? So we already got the A inverse here. So we already have the A inverse to be equals to -2, 1, 3/2, -1 all over 2. That is our A inverse. Now, what is the A inverse transpose? Then A inverse transpose is just the same as interchanging the rows and the columns. So -2, 1. And then here is 3/2 minus 1/2. Okay. So what can you see from that? The same thing, right? So it means that A inverse transpose is the same as A transpose. And then you do the inverse. Then you do the inverse. Understand? Now, this will bring us to the theorems here, which is theorem 1.5. Theorem. Now, let's A and B be invertible n by n matrices. The invertible n by n matrices. Now, number one, what we saw, A inverse is an invertible matrix. And A inverse, and then you do the inverse of it, then what you get is A. So to prove this is just the same as using the transpose. It's just similar to the similar. The proof is just similar. A inverse transpose is the same as A transpose. So we want to prove is that it's actually similar. Number two, A transpose is an invertible and A transpose and then inverse is the same as A inverse, and then you do the transpose. So that is what we can solve from there. And then lastly, number three, AB is an invertible matrix and AB inverse is the same as B inverse A inverse. AB inverse. So when you multiply the two matrices, then the inverse of the product of two matrices is the same as the inverse by A inverse. So we just saw this. So actually, this is similar to the one for transpose. The one for transpose. Okay. So we are not going to prove this. We just proven this using that example. There. Okay. Now let's now look at another theorem here. 1.6. If A1, A2, all the way to AP are invertible n by n matrices, then the product of A1 multiplied by A2 multiplied by A3 all the way to AP is also invertible n by n matrix. And A1, the product of A1, A2, A3, all the way to AP inverse is the same as starting from the last one, multiplying. So it is the same as AP inverse AP minus 1 inverse all the way to A2 inverse, then A1 inverse. It's actually just like this theorem. Has to, if there are 3, 4, or 5, then the product of all those matrices are still n by n matrices. When you get the inverse of them, then when you multiply the matrices and then you get the inverse, it's the same as getting the inverse and multiply n. So last one, inverse of the last one, second last, then up to the first. Okay, now let's look at cancellation 1.7, cancellation laws, cancellation laws. We let A, B, and C be matrices. Number one, let's start from left cancellation. Left cancellation law. Now, if A, B equals to AC and A is invertible, then B equals to C. So to prove this one is simple. If AB equals AC and A is invertible, that means we can get the inverse of that A. So to prove this is easy. So if we have AB equals to AC, say, so we can multiply this by the inverse and this one by the inverse here. Okay. So actually that one multiply by the inverse of that. Then this is the same as A inverse A multiplied by B equals to A inverse A multiplied by C. And then this is the same as IN B equals to IN C. And therefore B is equals to C. B is equals to C. So that is left cancellation. So you're cancelling from the left. Now, right cancellation, number 2. If AC equals to BC is invertible. Oh, sorry. If AC equals to BC and C is invertible, then A is equals to B. A is equals to B. So it's the same thing. So A, C multiplied by the inverse is the same as B, C multiplied by the inverse. Then A, C, C inverse equals B, C, C inverse there. Then therefore A, I, N is equals to B. I, N, then A is equals to Any question after that? Any question after that? Okay, let's look at 1.8 theorem. If A is an invertible n by n matrix, and the vector B is a vector in Rn, then the matrix equation Ax is equals to B has a unique solution X, which is equals to A inverse B. A inverse B. So if you still remember the matrix equation, so if you want to get the values of X, so the last time what we were doing is we were reducing A to reduce echelon form to get a value of X. And now, this to get a value of X, what you need to do is you multiply, you get the inverse of A, and then you multiply by B. X. So therefore, proof of this is if, so the proof, if X is equals to A inverse B inverse, then using the left cancellation, then it means that when you multiply by A, X is the same as A, and then multiply this one by A inverse. Right? So therefore, then AX is equals to A inverse of that. Then AX is equals to I. So then AX is equals to AX is equals to. So also, if you use the right cancellation, now if X is a solution of AX equals to B, then if you use also the left cancellation here, then when you multiply A inverse and A X here equals to A inverse B, then A inverse and then A X is the same as A inverse and then B. Then also I n X is equals to A inverse B. So therefore X is equals to A inverse B. So to get the values of X, then A inverse multiplied. So if you do that 2 by 2 matrix, then it is easy to get. Okay. All right, let's meet on Friday. Then we continue.
In exam next week or did it get pushed back?
Oh, I think it's next week. I need to check.
Okay.
I will email you guys.
All right.
Yep. Mhm.
I can send you.